So in chapter 15 here, we're going to be switching gears a little bit and talking about something other than just, right, these kind of straight up, here's your reagents, here's starting materials, here's our reaction. So we're going to learn a little bit more about something going on here, talking about orbitals again, right, kind of like we learned a little bit about at the beginning of Orgo 1, right? And in particular, we're looking at these p orbitals. We won't be going in as much depth as we would in a class like physical chemistry, but we are going to be discussing them again. So this might be a good opportunity early on to sort of review some of these molecular and atomic orbital concepts we learned about, right, these s and p orbitals. To start us off here, we're going to be discussing what we can do with these molecular orbitals. So something we're going to be learning about in a little bit is something called a pericyclic reaction, where we can do this internal reaction with alkenes and produce a ring, right? Like we've seen with some other intermolecular reactions. So here, depending on what conditions we use, right, on either side, right, we have EE hexadi2,4-ene, right? The same molecule on either side. What's changing here is the conditions that we're going to be using to transform them. So on the left, if we use heat, we get this reaction where the ends sort of close up on themselves, and we form the following transalkene. And if we use light, right, like we've seen in those radical reactions where we're adding on bromine, we're forming again an alkene, but this time it's cis, right? And we can see these methyl groups on, oops, I did that wrong, right? We're drawing the methyl groups on the same side, right? They're both pointing in the same direction, versus when we use heat, and they're pointing in opposite directions. Okay, and we're going to learn a little bit about how this comes to be. Okay, but to do that, we need to discuss molecular orbital theory. So in molecular orbital theory, some things we have to keep in mind, which I've kind of written up here, is, first of all, the number of atomic orbitals equals the number of molecular orbitals. So if we have 2 carbon atoms, we will have 2 molecular orbitals. And we're going to get to each of these rules as we kind of go along here, okay? And so if we're looking at our simplest alkene, right, just as ethene down below, and we're looking at the molecular orbital for ethene, what we want to do is we want to draw out the carbons. And right, we said the number of molecular orbitals equals the number of atomic orbitals, so we would have 2 molecular orbitals, okay? And so on each carbon here, we're going to write down our p orbitals, right? And if we remember from our discussion of p orbitals back in Orgo 1, we know they have these different phases, right? A filled in and a non-filled in phase, or red and blue, depending on how you're looking at it. And so here, right, we can see these orbitals are overlapping, right? This would be our bonding orbital, right, and we see we have this energy axis, right, on our y-axis here, which we say is the zero energy point, right? Because the whole thing with why molecules even form bonds in the first place is because they would like to be in a lower energy state, right? So our bonding orbital, right, is going to be lower energy, right, because it's more stable. And up above, right, we have our anti-bonding orbital, which again we talked about in Orgo 1, where the nodes are no longer lining up, or these orbitals are no longer lining up. And so what we can see here is that there is this sort of non-lining up of the phases, right? And so this is our anti-bonding orbital, which is higher in energy. And so, right, we have to fill in these electrons as well, and when we're counting our electrons, we're only counting the electrons that are present in our pi bond here, right? So there's just 2 electrons in this pi bond, and so when we're filling in our electrons, we can only fill in, right, just these 2, right? There's no electrons in the anti-bonding orbital. So all the energy is right below 0, right, which is the basis, again, of why things like to form bonds in the first place, okay? So this is our MO diagram. right, our molecular orbital diagram. And so to kind of keep going here with the terminology, which we'll keep using as we talk about this in class, so don't worry if this is kind of a lot of information at the beginning. We're going to go over this in a lot of detail in class too. So we have our bonding and antibonding molecular orbitals here, and so we can also call them our highest occupied molecular orbital, right, which we also refer to as our HOMO, and then we have our lowest unoccupied molecular orbital, which is our LUMO, LUMO. This is terminology just to say that, okay, this is the phase where we have the most, these are our highest electrons in a molecular orbital, and this is our lowest place where we have no electrons. This will be important later when we have more than just two molecular orbitals to look at, okay? Some other terminology we can also say is that when we have no overlap between orbitals, we would say that there is one node, right? And so for a bonding orbital, we have 0 nodes, okay? There's just a complete and total overlap between the phases, while up above, right, there's no overlap. And this terminology will be important moving forward, but I want to kind of put this all out here, okay? And I'm going to erase part of the screen here, right, so we have room to look at our other species here, which has more molecular orbitals. So I'm going to erase this. If you need to, you can maybe put this on a different page or something. That'll keep the sort of basis over here. So now we have a system with more than just two electrons. So we have 4 carbon atoms, right? So we have 4 molecular orbitals. So let's go ahead and put those down here. So these are kind of representing all the carbons. We're not going to worry about putting them in a zigzag formation, okay? This will make things a little simpler. I'll actually draw them out bigger. Okay. So now, right, we're going to do the same thing, and we're going to count up our electrons, okay? So on the side here, we're going to put down our electrons. So we know we have 4 electrons, right? 2 for each pi bond. So we can go ahead and put them in here, just like we would do over here. And so right now we can see that we have our electrons filled in, and so now we want to go ahead and fill in our molecular orbitals, okay? So we have 4 p orbitals, right, for our 4 carbon atoms here, right? So we do this for every single one, these kind of figure 8 p orbitals here, right? They're not 8s, right? These are representing the lobes on each carbon. And so we can go through and fill these in, right? And we know, again, we have 0 nodes on our first molecular orbital. We have 1 on the next, 2 on the next, and 3 on the next. So these nodes, right, kind of increase as we go along. And so for 0 node, that means all the orbitals have to be in phase. 1 node placed symmetrically in a molecule has to be like this, where we have, right, this de-alignment of phases here, right? 2 nodes means, again, symmetrically placed across the molecule, there are 2 gaps now, right, in our system. And 3 nodes means, right, there's total disalignment, where none of the orbitals overlap, okay? And so here is our LUMO, and here is our HOMO, right? Our highest occupied molecular orbital, and then our LUMO is our lowest unoccupied molecular orbital, okay? And what we can see here, we're looking at our molecular orbital, this, our highest occupied molecular orbital, looks a lot like butadiene down here, right? We have 2 phases overlapping, right? This one double bond. And this other phase, we have these 2 other orbitals overlapping with a node right in the middle here. This won't always apply, but generally our highest occupied molecular orbital is going to look a lot like our actual line angle structure, right? How our molecule looks in reality, okay? And again, we'll go into examples of why, right, these highest occupied molecular orbitals and lowest unoccupied molecular orbitals matter. Okay, we will get there. All right, so let's look at another example. Okay. So for our next example here, we're going to look at one more MO diagram. We're actually not going to worry about radicals. I forgot to remove this. Don't worry about radicals. And so for this next example, right, same thing, but this time we kind of have this odd number of molecular orbitals, right? Looking at our example over here to the right, we have 3 carbons with still 4 electrons, right? We have 2 from the lone pair and 2 on the p orbital, right? And we can see we have part of this energy diagram already filled in. And so here, right, our zero energy is always symmetrically placed. So here, a zero energy point, right, 0, right? And when I say zero energy, this is kind of relative to everything else, right? So our zero energy here is actually right in the middle. And so when we're filling up our electrons here, right, we have 4 electrons, right, from each of these conjugated electron systems, right, our lone pair and our pi bond. So we have this sort of placement. And so we're filling in the rest of our orbitals what actually happens now, right, is we have 0 nodes, we need 1 node here and 2 nodes here. There's not really a great way to get 1 node on this odd placed system, or odd numbered p orbitals, right? So what we actually have to do is, right, we can remove this middle one here and leave it blank. So this is how we can symmetrically place our orbitals. Right, so I would actually say there is, right, there's no middle p orbital there, or it's effectively not there, okay? And this kind of, again, looks like how our molecule looks like in reality, right? If we're looking at our propene, right, anion down below, right, you can do resonance, right? And so that negative charge is sort of placed across the molecule, right, on either side, which is kind of how it looks like in our highest occupied molecular orbital, and our lowest unoccupied molecular orbital is up above it, right? And so one other piece of terminology we're going to be learning, right, is we have, right, our bonding MO is down below, our anti-bonding is what's above the 0 point energy, and if we have a molecular orbital at the 0 point, we call this non-bonding. Just some terminology here that we'll get into a little bit later, okay? So I know, right, this is a lot, right? We're kind of learning and relearning some new stuff here with molecular orbitals. So we're going to, of course, cover this in class as well. So what we're going to do, as well as start thinking about reactions, we're going to go ahead and do another MO problem in class. We're looking at more electrons, okay? More molecular orbitals. So we'll start here in class.